In this highlight video, we're going to talk about nucleophiles. We've had them introduced before, but we'll talk about them in more depth here. After watching this video, you should be able to describe the properties of a strong nucleophile, and you should be able to look at a list of nucleophiles and rank them based upon their nucleophilic strength or their nucleophilicity. Like with leaving groups, a way to understand nucleophiles is to compare substitution reactions with acid-base reactions. Remember, in a substitution reaction, the electron pair on the nucleophile reacts with the carbon that's bearing the leaving group. The leaving group then comes off, taking the electrons from that bond with it to generate our product over here and the leaving group. If we look at an acid-base reaction, this time focusing on the base, we see that the base is using its non-bonding pair of electrons to form a bond with a hydrogen. That hydrogen or proton gives up its electrons to X to form the product, which is the conjugate acid plus the conjugate base. Groups that are good bases then tend to be good nucleophiles. It's not always true, but it's generally true. So stronger bases tend to be better nucleophiles. And remember that a strong base will be the conjugate base of a weak acid. Conjugate base of a weak acid. We will first focus on nucleophiles that have nucleophilic atoms that are roughly the same size or are the same atom. So when we say that atoms are the same size, we generally mean that they're in the same row of the periodic table. In these cases, nucleophilicity parallels basicity. These are three specific instances. If we have two nucleophiles with the same nucleophilic atom, the stronger base is more nucleophilic. For example, if we compare the nucleophilicity of hydroxide with the nucleophilicity of, this is a acetate or a carboxylate anion. It's the conjugate base of a carboxylic acid, right? Because the carboxylic acid is a stronger acid, this will be a weaker base. Water, which is the conjugate acid of hydroxide, is a weaker acid, so hydroxide is the stronger base. So hydroxide here is also the stronger nucleophile. Instance 2. A negatively charged nucleophile is always a stronger nucleophile than its conjugate acid. So here again, a good example is comparing the nucleophilicity of hydroxide to the nucleophilicity of water. Both species have non-bonding pairs of electrons, so they can behave as nucleophiles, but the stronger base, which is hydroxide, is going to be the stronger nucleophile. right? In fact, water is its conjugate acid, and the acid is the weaker nucleophile. The third instance here is that if we have atoms of roughly the same size, the more basic is the more nucleophilic. So this follows even when we have different atoms. So we looked at this when we were looking at acidity as well. So if we compare this methyl anion to, this is the amide anion, the conjugate base of ammonia, to hydroxide, to fluoride. We're just marching our way across the second row of the periodic table, looking at the conjugate bases of the possible acids. Because acidity increases as we go to the right, going across the periodic table, basicity increases when we go to the left. So as we go from right to left here, we get more basic and we make stronger nucleophiles. When we start comparing the strength of nucleophiles that have nucleophilic atoms that are of different sizes, meaning that they're on different rows of the periodic table, we're either going up or down the periodic table, it becomes more complicated. This type of comparison is affected by the solvent that the reaction is being carried out in. To understand this, we need to look at the types of solvents that are available. We can categorize solvents in two different groups. We have the polar aprotic solvents and we have the polar protic solvents. So let's look at the polar protic solvents first. When we say protic, what we mean is that these solvents have an OH group. These include water, these are alcohols, or carboxylic acids. The polar aprotic solvents do not have an OH. They have no OH. Some common aprotic solvents are acetone. This is a ketone. Acetone is found in fingernail polish remover. A common solvent for substitution reactions is dimethyl sulfoxide down here. Its abbreviation is DMSO. So DMSO is similar to acetone, but the carbon at the center of the molecule has been replaced with a sulfur. Another common solvent for substitution reactions is called dimethylformamide, or DMF. And it's listed right here. This is called an amide bond. All right, so those are some of the most common polar protic solvents for substitution reactions. How can solvent affect nucleophilicity? Well, the thing that it does is that solvents can be attracted to and encumber or surround different ions. So, for example, the polar aprotic solvents, in these drawings they're using acetone. Acetone, we know, has a polar carbon-oxygen bond. It makes a delta minus on the oxygen and a delta plus on the carbon. That minus on the oxygen can be attracted to a cation like sodium. So acetone molecules get attracted to and get organized around a sodium ion. So they can solvate cations, right, through an ion dipole interaction. However, Polar aprotic solvents are not good at solvating anions. The delta plus of that carbon is too surrounded, it's too sterically congested to be able to solvate anions. So here's a drawing on the right where bromide anions, they're surrounded by acetone molecules, but the acetone molecules are not organized around them. Polar protic solvents are good at solvating both cations and anions because, for example, water has a delta minus on the oxygen and delta pluses on both of the hydrogens. So water is good at solvating cations through this ion dipole interaction, and water can also solvate anions through hydrogen bonding interactions. If we run a substitution reaction using a halogen or halide as a nucleophile, if we run it in a polar aprotic solvent, then the halides are not solvated. Because of that, they're unencumbered and their reactivity follows their basicity. And so if we look at the basicity increases going this way, and so the nucleophilicity also increases from right to left. If we run the same reaction in a polar protic solvent, the solvents easily solvate especially the smaller, more basic anions. So solvation will increase as we go to a smaller anion. So as we go this way, so this has increased solvation. When we have an anion that's solvated, in order for it to react as a nucleophile, all of those solvent molecules need to be pushed out of the way so the anion can get to the electrophile. A nucleophile can get to the electrophile. So the more solvation, the more it slows down the reaction, and so the order of nucleophilicity reverses. So we have stronger nucleophilicity as the atoms get bigger because they're less solvated. So when we have atoms that are nucleophilic atoms that are directly above or below each other, their order of nucleophilicity can be reversed by changing the solvent. This slide shows some common nucleophiles. As we see on one side here, we have the negatively charged nucleophiles. Remember, negatively charged nucleophiles are generally stronger than are the neutral nucleophiles. And we know especially that negatively charged nucleophiles are stronger than their conjugate acid. So if we compare water with hydroxide, the stronger nucleophile. If we compare hydrogen sulfide over here with the thiolate anion, the thiolate anion is stronger over here. Two important nucleophiles on this table are these two carbon nucleophiles right here. And they are important because we can use them to form carbon-carbon bonds. Much of organic chemistry has to do with organic synthesis. And in order to build an organic molecule from a small molecule up to a big molecule, you need to be able to make carbon-carbon bonds. So an example here, we could just say, take chloroethane, and if we react that with this anion of the alkyne, this is called an acetylide anion. This is just a new nucleophile for us. So this can go here and can displace the chloride. And when it does that, we have now made a longer carbon chain. And this is going to be important as we go forward.